Hello everyone and welcome to Applied Engineering channel. Here we discuss the innovative ideas and concepts regarding thermodynamics. In the part 1 of this video we have seen and we have learned about cycle THX, and we learned about the cycle THX and its key features and how to download and install the software. In this video, we will move along and we will see how to run the software in different modes like its impose mode or simulate mode, and we will run one examples which is provided in this software. So let's dive into this software. So this is cycle DHX version 2. When we open this software, this is the interface of this software. And here we can see first is the file option where you can open a new file. And this is the options tab. Here first you have to set the unit reference state and evaporation and condenser pressure drop specifications. So here in the startup preference, first you will select the initial units in which you want to work and the type of input for the evaporator or condenser saturation conditions, like you want to input the temperature change in the condenser or evaporator or the pressure drop, and you have to select the reference state. So these are the already selected options, and here is the load and initial file. So it is no, do not load any file, and I will discuss later on why you need to load an initial file in this. So let's open a new file. So there are three tabs available in the new file. So the first tab is regarding the refrigerant selection. In the refrigerant selection, you can select a single compound fluid, you can select a predefined blend, or you can define your own new blend. For example, in the single compound fluid, you will just click it and it will show you the list of the single compound fluids. So this is the list of the single compound fluids in its library, and you can check the information regarding any fluid, and you will just click the info and you will see its basic info regarding critical properties and temperature, pressure and density. For the predefined blend, you will just see these are some predefined blends available in its library. And like this library is actually linked with the REFPROP 10.0 version. If you want to define a new blend, you can also define a new blend, and the maximum number of pure fluids you can use to define a new blend is 5. For example, I will select 5 pure fluids, and when I will select the 6, it will say that the maximum number of fluids exceed the limit. So you can select 5 pure fluids and you can make your own new blend. For example, I have selected these 5. You will just select the mass fraction or the mole fraction accordingly, and then you will store it, and it will store it into the predefined blends. For example, I will just name it R-111 or anything, and it will save this blend. And then when you will go to the predefined blend, you will see it is available and you can just select it. So we will just select pure compound ammonia and we will see what are the other tabs. After the refrigerant tab, there is the cycle options where there are different cycles available in this software. For example, single stage cycle, 2-stage with economizer, and 2-stage compression with intercooling, 3-stage economizer. And there are options like do not include liquid line or suction line heat exchanger, or the effectiveness of this heat exchanger. So we can see the single stage configuration. For the 2-stage economizer, it asks you about you want the same efficiency in both cycles, or you have to specify different efficiencies for the 2 stages. So you have to select one option. Similarly, this is the 2-stage compression with intercooling, and this is the 3-stage economizer. So first we will go to the single stage and then we will move for the cycle specifications. So here we can see this is the main tab. Here we have to define our cycle specifications. And here we have two modes like the impose mode or the simulate mode. So now I will discuss what is the difference between this impose mode or the simulate mode and how we can use this simulation software. So first what we will do, we will go to the file and we will go to the open. Here you will see there are different examples already given by the Cycle DHX software. This is the example of R-410 refrigerant. This is for AC test, and there are also different examples inside this folder. First we will go for the R-410A example and we will click open. So it will load all the data inside this example. You can see it has already selected the refrigerant R-410. When we will go for the cycle option, it has already selected the single stage cycle and it is not including the liquid line, suction line, heat exchanger. In the cycle specification tab, we can see it has already uploaded all the data from the file. So now we will see what is in the cycle specification tab. Here we can see it has already selected the impose mode, and for the heat exchanger representation it has selected the delta T. And first we will see what are the parameters it has already updated from the file. So we can see for the heat exchangers it has selected the configuration of cross flow, whereas it also has other configurations of counter flow and parallel flow. And this is the heat transfer fluid inlet temperature, which is usually air. So it has already updated the heat transfer fluid inlet temperatures and heat transfer fluid outlet temperatures for both evaporator and condenser. This delta T, which we have selected here that we will input, is the harmonic average temperature difference between the heat transfer fluid and your refrigerant, which is R-410A. So do not confuse this temperature difference between the temperature difference of this secondary fluid or heat transfer fluid. This is actually the temperature difference between the heat transfer fluid and the refrigerant, and this is harmonic average mean temperature difference. So for evaporator its value is updated as 9 from the file, and for condenser its value is updated from 7.30. Another important thing which it has also updated is the saturation temperature drop. So you remember that in the options we have to select the temperature or pressure specification for the condenser and evaporator. So as we have selected the saturation temperature option, so here you have to give it the saturation temperature drop. So here it has defined its value of 0.70 and 0.70 for both evaporator and condenser. For the superheat, it has defined the value of 5 degrees Celsius for the evaporator and subcooling value of 5 degrees Celsius for the condenser. Similarly, here we can see is the compressor box. Here it has defined the isoentropic efficiency of 0.7 and the volumetric and electric motor efficiency of 1, that is 100%. We can also switch this compressor configuration to maps. It has already built in maps of few compressors which we can see here. But for this example we will just switch to efficiency mode and we will use the same parameters as in this example. In this box you can see it has defined the cooling capacity of 11.81 kilowatt and the vapor line's pressure drop is assumed to be 0 for both the suction line and discharge lines. Also, the auxiliary power of indoor fan, outdoor fan and the power for controls is assumed to be 0. So this is the data provided in this example. Now we will learn what is the importance of this impose heat exchanger function. So this impose function performs a cycle simulation based on the user specified heat exchanger UA or delta T values and develops reference parameters for subsequent simulation with a different refrigerant or at different operating conditions. So each time we will check this established box, you can see it has enhanced the parameters. What the impose function do, as from its name it is implied that you will impose the values of this delta T and this saturation temperature drop in your simulation, and these values of delta T and this saturation temperature drop values will not simulate, they will remain fixed. So actually the impose mode is, it gives you the option of imposing your experimental data of your configuration of your heat exchangers, evaporator and condenser, so that you can input that data and run this simulation as a reference run and check it that the results are verified or the results match with your experimental data. So these are the values in this file which we have uploaded are from the experimental generated results. So when we will check it, it will establish reference parameters, and here we can see it has already updated the heat exchanger configuration, or you can say that its inner diameter values, its length, number of tubes per circuit and number of circuits. And here it has calculated the heat transfer area for the evaporator and the condenser. So here actually you have to enter your experimental data or your laboratory data, and you will run it in the impose mode, and then you will verify its results of UA and pressure drops against your experimental data. And when they are verified and when they are comparable, you can say that this simulation is now giving you the exact and accurate results as per your experiment. So this is what we do in the impose run. We run it in the impose mode, and let's see what will happen. So after this you will just go to the run simulation and you will run it. So here we can see we have generated the results from the impose mode, and this is the summary of the results. So here we can see that it has defined that it is an imposed run based on the delta T and pressure drop, and it has calculated for the single stage cycle. It will define first the input data which we have given to it. So it is the input data, the configuration data, and then is the thermodynamic cycle results. So these are all the state points results. Then it gives the compressor and system results, the compressor power, COP cooling and COP heating values, compressor suction volume flow rate, and at the end you can see is the heat exchanger results which you have to verify from your experimental data, that is the refrigerant mass flux in the evaporator and the condenser, and the overall heat transfer coefficient values in the evaporator and the condenser. So actually in the impose run, what you have to do, you have to run it and you have to verify that these values are as per with your experimental results. These points are as per your experimental values, and the saturation temperatures of the condenser and the evaporator are as per your experimental values. If you do not have any experimental or laboratory facility, so you can use these example files which are already given by cycle DHX, and these are already validated results. Another thing about the impose run, that it is highly recommended to carefully examine the input data to the impose option simulation run and see its simulation results, since the unrealistic input data and results may lead to unreliable results and circuit optimization for the subsequent simulate runs. So the first input parameters that merits the verification of our impose run is the verification of this delta t or UA value. So if you will not put the right delta t or UA value as per your experimental data, you will not get a good reference run. For a given temperature profile of the heat transfer fluid, a properly selected delta T value results in refrigerant saturation temperature in heat exchanger that will match the value of the measured in the laboratory. Thus, the user can adjust the input delta T to obtain the agreement between the simulated and the measured saturated temperature values. Here we can see that when we have checked the established reference parameter, it has generated these two boxes. So the first box is the heat exchanger parameters, which it will calculate for every run, and it will calculate the refrigerant mass in the evaporator and condenser and the refrigerant side thermal resistance values. So these values will change when you will change the conditions or refrigerants. Whereas these are the reference parameters which we have just established. So these reference parameters will remain same. And what are in these reference parameters is the heat transfer fluid side thermal resistance values for the evaporator and the condenser. And as you know, because the refrigerant will change but the heat transfer fluid will remain same, so there will be not much difference in the thermal resistance values of the high temperature fluid. So for our reference parameters, these values will remain same as it is, and here it has calculated the imposed pressure drop divided by the simulated pressure drop values for the evaporator and the condenser. And these values are usually greater than 1, which means that our experimental result has more pressure drop as compared to our simulated pressure drop, because in the experimental results we have also considered the U bands in the configuration, whereas in the simulated results we don't consider the U bands for the double pipe heat exchangers. After running in the impose mode and establishing the reference parameter, we will move towards the simulate mode. And then in the simulate mode, we will run the simulation. The simulate option simulates the delta T or UA values. And in the simulate modes, now the user can select or change the compressor efficiencies or maps. Also in the simulate mode, you can see you can change the heat transfer fluid temperatures and superheat subcool values. When you will optimize the number of circuits, it will increase the COP value of the cycle by optimizing the number of circuits. So these things you can do when you are running it into the simulation mode. So here you can see the results have already generated, and in the simulate mode you can see the simulate heat exchanger UA and pressure drop single stage, and first it will give you the input data. So here you can see it is not giving you the configuration or gray data, which you cannot change now because you have already run a reference run and impose run regarding to your configuration, which is now fixed and which will not change. And now you are doing simulation, and in simulation you have These options which you still change is the configuration, is the heat transfer fluid inlet and outlet temperature, superheating and subcooling values, the optimize number of circuits, or you can change the compressor efficiencies and these other parameters. So here let's see what are the results of this simulate mode. You can see this is the input data, and then comes the thermodynamic cycle data. After that comes the compressor data and is the heat exchanger results. So here you can see the results is now populated where we have refrigerant mass flux and delta T values and UA values, refrigerant site thermal resistance values and saturation pressure drop. So the difference between the simulate mode and the impose mode is that in the impose mode it imposed the value of delta T and it imposed the value of saturation pressure drops. Whereas in the simulate mode, it has simulated these values and these can change because it is the same refrigerant and the same condition we have simulated as imposed. So there is not much difference in these values. But now what we will do, we will try to simulate it for another refrigerant and then we will see how these values change. So let's simulate it for another refrigerant R-32. You can also save this file by clicking on the save, copy the result data or print it. So I will just save it for the comparison and I will name it R-410A data. Now what I will do, I will just go into the refrigerant and I will select a single compound fluid that is R32. So we will go to R32 and double click it to select it. Now you can see our refrigerant has changed, but all the parameters are similar. Now we will run it and it will simulate it for R32. Here you can see the results are generated for R32. So we will just compare these results with the results of R410. So we will save this data and then we will compare it with R410 data. So this is R410 data and this is R32 data. And now we will just compare these results. So for R410, we can see that the refrigerant mass flux values, delta T values, UA values, refrigerant site thermal resistance values, and saturation pressure drop values. For R32, similarly, we can see these values, refrigerant mass flux values, delta T values, UA values, and refrigerant site thermal resistance values. So we can compare that these values have been changed. For example, for the refrigerant mass flux, the value for R32 is less as compared to R410. Similarly, the delta T values are increased for R32. And you can say like the saturation pressure drop values are more for R410 as compared to R32. Also, you know that R32 is the best refrigerant, so you can see the COP values. So COP cooling and COP heating values for R32 is 5.423 and 6.423, whereas for COP cooling and heating values for R410 are 5.350 and 6.350. So you can see the COP values of R32 are greater than the COP values R410. So this is how you can do the simulation of any refrigerant. If you want to change some other conditions, like you want to change the heat transfer fluid temperature, you want to increase or decrease the superheat values, or even you can change the cooling capacity values and you want to simulate it, now you can simulate it. For example, let's we want to change the cooling capacity from 11 to 10 kilowatt, and we want to see how the results will vary. So here it has generated with the cooling duty of 10 kilowatt, and it has changed the refrigerant mass flux, delta T, UA, refrigerant site, thermal resistance and saturation drop values, as well as the COP, heating, cooling, and all the state points have been changed. So this is how you can do this run. Another thing is how you can see the results. First is in this display results, you can see the summary of the results which it gives when it completes the simulation, and you can also see the system schematic. So in this system schematic you can see different points. So these are the evaporator outlet temperature after superheat, and then this is the liquid line, suction line, heat exchanger, which we are not using in this cycle, and then the compressor inlet, compressor suction line, then compressor discharge line, and then the inlet of the condenser, outlet of the condenser subcooling, and then so on, expansion valve inlet and expansion valve outlet. You can also change and see, instead of temperature, the pressure values, the density values, the enthalpy values, or the entropy values, whichever you like. Another thing is the TS and the pH diagram. So these are the TS and the pH diagram of the following circuit. You can also modify these diagrams. For example, if you want to change the colors of the vapor line and the liquid line and the process line, so you can just do it as per your requirement. You can change the font size, you can change the axis from linear to log, you can add the grid lines, you can increase the font size, everything you can do. So it will just alter it as per your requirement. So another thing in this result section is the line sizing. So with these results, it also provides you the line sizes of the vapor compression cycle. For example, it provides you a list of outside diameter values. So anything you can select depending upon the vapor velocity or the liquid velocity. Depending on these velocities, you can select the diameter of your pipelines. So this was all regarding the impose run and simulate run, and in the next videos I will try to put some more examples. If you have any question, please ask in the comment box. I would love to answer your questions. Please like and subscribe my channel if you like more updates and videos like this. This is the only way of supporting me. Thank you very much.